Environmental pollution is a major global issue, and understanding its different types, causes, and impacts is crucial for UGC NET JRF environmental science preparation. Pollution refers to the introduction of harmful substances or pollutants into the environment, which disrupts the natural balance. There are several types of pollution, including air, water, soil, and noise pollution, each with distinct causes, effects, and management strategies. Air pollution. This type of pollution occurs when harmful gases like carbon monoxide (CO), sulfur dioxide, SO2, nitrogen oxides (NOx), particulate matter (PM), and volatile organic compounds (VOX) are released into the atmosphere, primarily due to industrial emissions, vehicle exhaust, and agricultural activities. The effects include respiratory diseases, global warming, acid rain, and ozone depletion. Management strategies include reducing emissions, using cleaner fuels, adopting green technologies, and promoting renewable energy sources. The Clean Air Act in various countries aims to regulate air pollution and improve air quality by setting air quality standards. Water pollution. Water pollution occurs when harmful substances like chemicals, heavy metals, and pathogens contaminate water bodies such as rivers, lakes, and oceans. Sources include industrial discharges, agricultural runoff, untreated sewage, and plastic waste. The consequences include the destruction of aquatic ecosystems, the spread of waterborne diseases, and the contamination of drinking water sources. Water management strategies focus on treating wastewater, promoting water conservation, and enforcing regulations on industrial effluents. The Clean Water Act in the U.S. regulates water pollution and aims to restore and maintain the integrity of the nation's waters. Soil pollution. Soil pollution is caused by the accumulation of hazardous chemicals, such as pesticides, heavy metals, and industrial waste, in the soil. This leads to the degradation of soil quality, loss of fertility, and harm to plant and animal life. Soil pollution can be managed through the use of organic farming methods, the reduction of chemical fertilizers and pesticides, and proper disposal of industrial waste. Bioremediation techniques, where microorganisms are used to degrade pollutants, are also employed for soil decontamination. Noise pollution. Noise pollution refers to excessive noise levels that disturb the natural environment and human health. Major sources include transportation systems, industrial activities, and urbanization. Chronic exposure to high noise levels can lead to hearing loss, cardiovascular diseases, and psychological disorders. Noise pollution can be mitigated by using noise barriers, regulating sound emissions, and promoting urban planning that reduces noise exposure. Waste management. Waste management involves the collection, transport, and disposal of waste materials in an environmentally responsible manner. Municipal solid waste (MSW), hazardous waste, and electronic waste (e-waste) are significant waste streams that need to be properly managed. Techniques like recycling, composting, and waste-to-energy technologies are essential for reducing the environmental footprint of waste. Landfills, although common, have negative environmental impacts such as leachate formation and methane emission, which contribute to soil and air pollution. Environmental laws and policies. Several national and international laws and policies have been established to address environmental pollution and promote sustainable development. The Kyoto Protocol and Paris Agreement aim to combat climate change by reducing greenhouse gas emissions. National Environmental Protection Acts, such as the Environment Protection Act, 1986, in India, provide a legal framework for pollution control and environmental conservation. Sustainable practices. To mitigate the environmental impact, sustainable practices such as green energy solutions, zero waste policies, and sustainable agriculture are being promoted. The concept of a circular economy, where resources are reused and recycled, is gaining momentum as a solution to pollution and waste management. Environmental education and awareness programs also play a vital role in encouraging individuals and communities to adopt eco-friendly practices. Previous year questions. What is the primary cause of air pollution in urban areas? Answer: industrial emissions and vehicle exhausts. Year: 2021. Which of the following pollutants is mainly responsible for the depletion of the ozone layer? A. Carbon dioxide. B. Sulfur dioxide. C. Chlorofluorocarbons, CFCs. D. Nitrogen oxides. Answer: C. Chlorofluorocarbons, CFCs. Year: 2020. Which of the following is not a method for controlling water pollution? A. Sewage treatment. B. Reducing the use of fertilizer. C. Industrial discharge control. D. Increased use of plastic bags. Answer: D. Increased use of plastic bags. Year: 2019. What are the effects of noise pollution on human health? Answer: Noise pollution leads to hearing impairment, stress, and cardiovascular diseases. Year: 2021. Which legislation regulates the discharge of pollutants into water bodies in India? A. The Air Prevention and Control of Pollution Act. B. The Water Prevention and Control of Pollution Act. C. The Environment Protection Act. D. The Wildlife Protection Act. Answer: B. The Water Prevention and Control of Pollution Act. Year: 2020. What is the main objective of the Paris Agreement? A. To protect wildlife. B. To reduce global carbon emissions. C. To reduce deforestation rates. D. To regulate water pollution. Answer: B. To reduce global carbon emissions. Year: 2022. This lecture is designed to cover the key aspects of environmental pollution and management, with relevant content and previous year questions included to help you grasp the most important concepts for your UGC NET JRF environmental science exam. Let me know if you need more lectures or any other topics. You said, data interpretation sources. ChatGPT said. Data interpretation, sources, methods, and application. Data interpretation is a critical skill in various scientific fields, including environmental science. It involves analyzing data to derive meaningful insights and make informed decisions. In the context of UGC NET JRF environmental science, data interpretation is essential for understanding environmental trends, pollution levels, and the effectiveness of policies. Sources of data for environmental science. Data in environmental science can be sourced from a variety of methods and tools. These sources are essential for generating the data used in analysis and interpretation. Government agencies and reports. Government bodies such as the Central Pollution Control Board (CPCB) and the Environmental Protection Agency (EPA) regularly publish reports on air quality, water quality, waste management, and climate change. These reports are based on extensive data collection and monitoring programs. For example, the CPCB in India monitors air pollution levels in major cities, and the EPA provides detailed reports on environmental quality across the U.S. Satellite imagery and remote sensing. Satellite imagery is widely used in environmental studies to monitor large-scale changes such as deforestation, urban sprawl, and land use changes. Remote sensing technology provides data on land surface temperature, vegetation index, and pollutant dispersion. Agencies like NASA and ISRO, Indian Space Research Organization, offer valuable satellite data for monitoring environmental changes. Field studies and surveys. Field data is collected through direct measurements and observations in the field. Environmental scientists often conduct surveys to assess pollution levels, biodiversity, and soil quality. For example, water samples might be collected from various sources to measure levels of pollutants such as nitrates or heavy metals. Academic and research institutions. Universities and research institutions also generate large amounts of environmental data through independent studies, experiments, and long-term monitoring programs. Such data is often shared in academic papers, journals, and environmental impact assessments. Environmental sensors and monitoring stations. Environmental sensors deployed in specific areas provide real-time data on air and water quality, noise levels, and radiation. These sensors are often installed in cities, industrial zones, and sensitive ecosystems. Monitoring stations track environmental parameters such as CO2 levels, particulate matter, and temperature. Non-governmental organizations (NGOs) working in environmental conservation and climate change often conduct surveys and studies to generate data related to specific environmental concerns. They might focus on biodiversity loss, water scarcity, or pollution control. These datasets are valuable for understanding local and global environmental trends. Methods of data interpretation. Once the data is collected, various methods are used to interpret the results. These methods help transform raw data into useful insights that can guide decision-making. Descriptive statistics. Descriptive statistics summarize the basic features of the data, such as mean, median, mode, range, and standard deviation. For example, the mean value of air pollution levels across several cities can provide a snapshot of the pollution intensity. Graphical representation. Graphs such as bar charts, line graphs, and pie charts are often used to represent environmental data visually. These charts make it easier to identify trends, compare variables, and interpret complex data. For example, a bar chart could show the change in water quality parameters over time, helping to identify any patterns or anomalies. Correlation analysis. Correlation analysis examines the relationship between two or more variables. In environmental science, this could involve assessing the correlation between temperature rise and CO2 concentration in the atmosphere. Pearson's correlation coefficient R is often used to measure the strength and direction of these relationships. Regression analysis. Regression analysis is used to predict the value of one variable based on the value of another. For example, regression analysis could predict the concentration of pollutants in water bodies based on the industrial activity in surrounding areas. Linear regression is often used in environmental data interpretation to predict future trends. Time series analysis. Time series analysis involves studying data points collected or recorded at specific time intervals. This method is particularly useful in environmental science for understanding long-term trends, such as changes in temperature over several decades or shifts in species populations due to climate change. Geospatial analysis. Geospatial analysis uses geographic information systems (GIS) to analyze spatial data. For example, GIS can be used to analyze land cover changes, assess deforestation, or identify areas vulnerable to flooding. It allows environmental scientists to interpret data in a spatial context, helping in planning and policy making. Multivariate analysis. Multivariate analysis is used to interpret data with more than two variables. This technique helps in understanding complex relationships and interactions among multiple factors. For example, it can be used to analyze the combined impact of industrial activity, urbanization, and climate change on the health of an ecosystem. Statistical significance testing. Statistical tests, such as the t-test or chi-square test, help determine whether observed patterns in the data are statistically significant or due to random chance. For example, the t-test could be used to compare pollution levels between two cities, while the chi-square test could assess the relationship between land use and biodiversity loss. Application of data interpretation in environmental science. Data interpretation in environmental science is crucial for understanding the status of ecosystems, identifying pollution sources, and assessing the effectiveness of environmental policies. Some key applications include environmental monitoring and pollution control. Data interpretation is used to monitor pollution levels in air, water, and soil, identify hotspots, and recommend control measures. For example, interpreting air quality index (AQI) data helps in identifying areas that exceed safe pollution thresholds, prompting policy interventions. Climate change studies. Data interpretation plays a significant role in climate change research. Analyzing temperature and precipitation trends, as well as greenhouse gas emissions, helps predict future climate patterns and assess the impact of climate change on ecosystems. Biodiversity conservation. Data interpretation is essential in biodiversity conservation. By analyzing species population data, environmental scientists can determine the status of endangered species, assess habitat destruction, and recommend conservation strategies. Environmental policy and decision making. Data interpretation provides the evidence needed for creating environmental policies and regulations. It helps policymakers understand the current environmental situation, set goals for pollution reduction, and allocate resources for environmental protection. Previous year questions. Which of the following methods is primarily used to interpret environmental data related to climate change? A. Regression analysis. B. Time series analysis. C. Geospatial analysis. D. Descriptive statistics. Answer. B. Time series analysis. Year 2020. What does Pearson's correlation coefficient measure in environmental studies? A. The strength and direction of the relationship between two variables. B. The standard deviation of the data. C. The probability of environmental degradation. D. The frequency of environmental events. Answer. A. The strength and direction of the relationship between two variables. Year 2019. Which method is used to predict future trends based on existing environmental data? A. Time series analysis. B. Descriptive statistics. C. Regression analysis. D. Statistical significance testing. Answer. C. Regression analysis. Year 2021. Which of the following sources is a primary method for collecting environmental data related to air pollution? A. Field studies. B. Satellite imagery. C. Monitoring stations. D. Academic papers. Answer. C. Monitoring stations. Year 2022. What is the main objective of geospatial analysis in environmental science? A. To assess land use and ecosystem health. B. To analyze time-based trends in temperature. C. To measure pollutant concentrations in water bodies. D. To predict future trends in biodiversity loss. Answer. A. To assess land use and ecosystem health. Year 2021. Which type of data interpretation method is used to visualize pollution levels across different regions in the form of a map? A. Geospatial analysis. B. Time series analysis. C. Regression analysis. D. Descriptive statistics. Answer. A. Geospatial analysis. Year 2020. This lecture covers the essential aspects of data interpretation in environmental science, including sources of data, methods of analysis, and practical applications. The previous year questions will help you focus on key areas likely to appear on your exam. Let me know if you'd like more detailed topics or specific lectures. You said. Acquisition and classification of data. ChatGPT said. Acquisition and classification of data in environmental science. Data acquisition and classification are fundamental processes in environmental science, essential for effective analysis, interpretation, and decision making. Understanding how data is collected, acquisition, and categorized classification is crucial for environmental studies, where precision and accuracy play a vital role in deriving actionable insights for policy and management. Acquisition of data. Data acquisition refers to the process of gathering raw information from various sources to monitor environmental parameters, assess conditions, and track changes over time. This data can come from a variety of methodologies, tools, and technologies. Field surveys and observations. Field surveys are one of the most direct methods of data acquisition in environmental science. Researchers conduct on-site visits to collect data about physical conditions, biological diversity, and environmental factors. For instance, data on soil composition, water quality, air pollution, and vegetation health are often collected through visual inspection and sampling. Field studies are crucial for collecting real-time and localized data that may not be available through secondary sources. Remote sensing and satellite imaging. Remote sensing technologies, including satellites and drones, allow researchers to acquire large-scale environmental data. These tools capture information about land use, deforestation, vegetation cover, and water bodies over vast areas. Remote sensing is particularly useful in monitoring changes in the environment that are too large or difficult to study through ground-based methods. Satellites equipped with sensors can provide data on temperature, atmospheric conditions, pollution, and more. Environmental monitoring stations. Many environmental variables, such as air quality, water quality, and temperature, are continuously monitored through environmental sensors placed at fixed locations. Monitoring stations are often set up by governmental and non-governmental organizations in key locations, such as urban centers, industrial areas, or natural reserves. These stations provide real-time data, which is often used to track pollution levels, climate variations, or ecosystem changes over time. Sensor technologies and IoT. Internet of Things IoT devices and environmental sensors provide another avenue for continuous data collection. These devices can measure various environmental parameters like air and water quality, noise pollution, and soil moisture. The data collected is often transmitted in real time, allowing for near instantaneous monitoring and reporting. For example, a network of water sensors might be installed along a river to track pH levels, turbidity, and contaminants. Laboratory analysis. Data can also be obtained through laboratory analysis. Environmental samples, e.g., soil, water, air, or biological samples, are collected in the field and brought to a laboratory for detailed analysis. For instance, water samples may be tested for chemical contaminants, while soil samples can be analyzed for nutrient content or heavy metals. This method provides highly accurate, but typically less frequent, data points. Governmental and institutional databases. Many government agencies and international organizations maintain databases with environmental data that has been collected over several years. These datasets often include historical information on air quality, climate patterns, pollution sources, and biodiversity indices. They are vital for tracking long-term environmental trends and assessing the effectiveness of environmental policies and interventions. Environmental trends and assessing the effectiveness of environmental policies and interventions. Crowdsourcing and citizen science. Crowdsourcing, where ordinary citizens participate in data collection, is a growing trend in environmental science. Apps and online platforms allow people to report environmental observations, such as sightings of endangered species, local pollution levels, or unusual weather events. While not always scientifically precise, crowdsourced data can provide valuable insights, particularly in areas with limited research infrastructure. Classification of data. Once data is acquired, it must be classified in a systematic manner to facilitate analysis and interpretation. Classification refers to the categorization of data into meaningful groups or types, which allows researchers to identify patterns, correlations, and trends. Environmental data can be classified in various ways depending on its nature and intended use. Categorization by source. Data can be classified based on its source, such as field-collected data, satellite data, laboratory results, or data from monitoring stations. This classification helps to assess the reliability, accuracy, and scope of the data. For instance, satellite data might be classified as remotely sensed data, while field data could be categorized as direct observational data. Categorization by temporal aspect. Environmental data can be classified based on time, such as real-time data, historical data, or predictive data. Real-time data provides immediate insights into current environmental conditions, such as air quality measurements or light pollution levels. Historical data offers a long-term view, such as past climate patterns or previous pollution events, which are used to track trends and predict future conditions. Predictive data often comes from models that use current and historical data to forecast future environmental changes. Categorization by spatial aspect. Environmental data is often classified based on spatial characteristics, such as local, regional, or global data. Local data focuses on specific locations or ecosystems, such as a river or forest reserve. Regional data might cover a larger geographical area, such as an entire watershed or climate zone. Global data encompasses broader environmental phenomena, such as atmospheric temperature changes or global biodiversity indices. Categorization by environmental parameter. Data is often classified according to the environmental parameter it measures. Common categories include air quality data, includes parameters such as particulate matter PM2.5, PM10, sulfur dioxide, CO2, nitrogen oxides, NOx, carbon monoxide, CO, ozone levels, and greenhouse gases CO2, methane. Water quality data, includes parameters such as pH, turbidity, dissolved oxygen, heavy metals, nitrates, phosphates, and biological oxygen demand pod. Soil quality data, includes soil moisture, temperature, pH, salinity, and nutrient content such as nitrogen, phosphorus, and potassium. Biodiversity data, includes species population counts, species diversity indices, and habitat assessments. Categorization by measurement type. Environmental data can also be classified according to the type of measurement used to collect it. Quantitative data, numerical data that can be measured and expressed in numbers, such as pollution concentration, microgram per cubic meter temperature, degree C, or rainfall. Qualitative data, descriptive data that provides non-numerical information, such as species behavior, presence of rare species, or visual assessments of habitat conditions. Categorization by purpose. Data can also be classified by the purpose it serves in environmental management or policymaking. Some common purposes include monitoring and surveillance, data collected to monitor the ongoing state of the environment. Impact assessment, data used to evaluate the environmental impact of specific activities, such as construction, mining, or industrial operations. Modeling and forecasting, data used to develop predictive models that forecast environmental changes, such as climate models or ecosystem services models. Decision support, data used to inform environmental policies, regulations, and management strategies. Importance of data acquisition and classification. Accuracy and reliability, proper acquisition and classification ensure that data is accurate, reliable, and suitable for the intended analysis. For instance, poor data classification could lead to incorrect conclusions, especially when environmental decision-making is based on flawed data. Efficient analysis, when data is well classified, it can be easily accessed and analyzed using appropriate statistical or computational methods. This leads to more efficient and meaningful insights, which is crucial for timely decision-making in environmental management. Facilitation of comparisons. Categorized data allows comparisons across time, space, and environmental parameters. For example, comparing air quality data across different cities or years can help identify pollution trends, and classifying biodiversity data helps in assessing species loss or habitat degradation. Policy formulation. Accurate acquisition and systematic classification of data are essential for formulating effective environmental policies. Reliable data is required to support policy decisions on issues such as pollution control, wildlife conservation, and climate change mitigation. Previous year questions. What is the primary goal of data classification in environmental science? A. To organize data into meaningful categories. B. To collect data in large quantities. C. To increase the complexity of the data. D. To visualize data trends. Answer. To organize data into meaningful categories. Year, 2021. Which of the following is a key benefit of remote sensing for environmental data acquisition? A. Ability to collect large-scale data over time. B. Limited to terrestrial data collection. C. Involves high fieldwork effort. D. Data collection is restricted to urban areas. Answer. Ability to collect large-scale data over time. Year, 2020. Which of the following is an example of quantitative environmental data? A. Species biodiversity index. B. Concentration of particulate matter in the air. C. Water color assessment. D. Visual inspection of forest health. Answer. B. Concentration of particulate matter in the air. Year, 2019. Which data acquisition method is most appropriate for monitoring air pollution in real time? A. Field surveys. B. Satellite imagery. C. Monitoring stations. D. Crowdsourced reports. Answer. C. Monitoring stations. Year, 2021. What type of environmental data is collected via Internet of Things IoT sensors? A. Satellite imagery. B. Real-time air quality readings. C. Historical water quality data. D. Visual species population counts. Answer. B. Real-time air quality readings. Year, 2020. How is environmental data typically classified when it pertains to monitoring the health of an ecosystem over time? A. By spatial aspect. B. By environmental parameter. C. By temporal aspect. D. By measurement type. Answer. C. By temporal aspect. Year, 2021. This lecture covers the key aspects of data acquisition and classification in environmental science, explaining the methods, types, and importance of both processes. It also includes practical applications and examples to prepare you for the UGC NET JRF exam. You said. Quantitative and qualitative data. ChatGPT said. Quantitative and qualitative data in environmental science. In environmental science, data is fundamental to understanding and interpreting environmental conditions, trends, and patterns. This data is typically classified into two broad categories: quantitative data and qualitative data. Each of these types of data has distinct characteristics, uses, and methods of collection. Understanding the difference between them is crucial for selecting the appropriate data for analysis, making informed decisions, and generating reliable results. Quantitative data. Quantitative data is data that can be measured and expressed numerically. This type of data provides objective, precise, and measurable information that can be analyzed statistically. In environmental science, quantitative data is vital for understanding environmental changes, monitoring pollution levels, assessing biodiversity, and evaluating ecosystem health. Characteristics of quantitative data. Numerical. Quantitative data consists of numbers that represent quantities or amounts. For example, temperature, rainfall, pollutant concentration, and population size. Measurable. Quantitative data is obtained through measurements that yield numeric values. This data is precise and can be subjected to statistical analysis. Objective. The measurement process is standardized, reducing the potential for personal bias or interpretation. For instance, the amount of carbon dioxide in the air can be measured in parts per million ppm. Continuous or discrete. Quantitative data can be continuous data that can take any value within a range, such as temperature, pH, or rainfall, or discrete data that can only take specific, distinct values, such as the number of species in an area or the count of pollutants. Methods of collecting quantitative data. Instruments and sensors. Devices such as thermometers, pH meters, and air quality sensors are used to collect quantitative data on environmental variables. For instance, air pollution levels are often measured using sensors that quantify concentrations of particulate matter PM2.5, PM10, or gases like carbon dioxide CO2 and nitrogen oxides NOx. Sampling. Data can be collected by taking representative samples from an environmental medium, e.g., water, soil, or air. The concentration of pollutants or nutrients in water samples can be measured quantitatively in a laboratory. Monitoring stations. Automated environmental monitoring stations continuously record data, such as atmospheric temperature, rainfall, and air quality parameters. This data is collected in real time and is often used for climate studies, pollution control, and disaster prediction. Remote sensing. Satellite imagery and aerial photography provide quantitative data about land cover, deforestation, and changes in vegetation over time. For example, the area of forest cover can be measured in square kilometers from satellite images. Examples of quantitative data in environmental science. Temperature. Air or water temperature is measured in degrees Celsius or Fahrenheit and used to study climate change, biodiversity, and ecosystem dynamics. Air quality. The concentration of pollutants like carbon monoxide, CO, sulfur dioxide, CO2, and ozone O3 in the atmosphere is measured in parts per million ppm or micrograms per cubic meter, microgram per cubic meter. Rainfall. Rainfall is measured in millimeters and is critical for studying hydrological cycles, droughts, and water availability. Species population. The number of individuals of a particular species in an area is a quantitative measure used in biodiversity assessments and conservation efforts. Soil nutrients. The concentration of nitrogen N, phosphorus P, and potassium K in the soil, measured in milligram per kilogram, is crucial for assessing soil fertility and land management practices. Analysis of quantitative data. Quantitative data can be analyzed using various statistical techniques, including measures of central tendency mean, median, mode dispersion variance, standard deviation, and correlation analysis. Environmental data is often subjected to time series analysis to detect trends and patterns over long periods, e.g., rising sea levels, increasing temperatures. Inferential statistics such as t-tests, chi-square tests, and regression analysis are used to draw conclusions or make predictions based on quantitative data. Qualitative data. Qualitative data, on the other hand, refers to descriptive data that characterizes qualities or attributes of a phenomenon. This type of data provides a deeper understanding of environmental conditions by capturing non-numeric information that cannot be easily measured in numbers. Qualitative data is essential in environmental science for capturing complexity, context, and human factors that influence environmental systems. Characteristics of qualitative data. Descriptive. Qualitative data is used to describe characteristics, qualities, or phenomena that do not have a numerical representation. Examples include observations of species behavior, environmental conditions, or community perceptions. Categorical. The data is often classified into categories, such as types of vegetation, e.g., forest, grassland, land use, e.g., urban, agricultural, or pollution sources, e.g., industrial, vehicular. Subjective. Since qualitative data relies on interpretation and observation, it may be influenced by the researcher's perspective, making it more subjective than quantitative data. Non-measurable. Unlike quantitative data, qualitative data does not have an inherent numerical scale and cannot be directly measured. It requires interpretation, often through text, interviews, or visual representation. Methods of collecting qualitative data. Field observations. Qualitative data is often collected through direct observation in the field. Researchers may observe the behavior of animals, the condition of ecosystems, or changes in the landscape. Interviews and surveys. Interviews with local communities, stakeholders, or experts can provide valuable qualitative data about environmental issues, community perceptions, and environmental changes. Focus groups. Focus groups are used to gather opinions and attitudes on environmental topics from a group of people, such as how local communities perceive pollution or climate change. Textual and visual analysis. Qualitative data can also be derived from the analysis of text, e.g., policy documents, news reports, or visual material, e.g., photographs, videos that describe environmental conditions or events. Examples of qualitative data in environmental science. Ecosystem health. Descriptions of an ecosystem's health, such as the presence or absence of certain species, the condition of a coral reef, or the degradation of a wetland, are qualitative. Species behavior. Observing animal behavior, such as migration patterns, mating rituals, or foraging behavior, provides qualitative insights into biodiversity and ecosystem functioning. Community perceptions. How local populations view environmental issues, such as the impacts of climate change, deforestation, or industrial development, is qualitative data gathered through surveys or interviews. Land use. Descriptions of land use types, such as residential, industrial, or conservation areas, help in understanding land cover changes, urbanization, and habitat fragmentation. Analysis of qualitative data. Thematic analysis. Qualitative data is often analyzed by identifying patterns, themes, or categories that emerge from the data. For instance, interviews with local communities might reveal common concerns about pollution or resource management. Content analysis. This method involves analyzing written or visual material to identify specific themes or recurring patterns. For example, analyzing newspaper articles might reveal public discourse around climate change. Narrative analysis. In this approach, researchers look at the stories or narratives that individuals or groups tell about their environmental experiences, helping to understand how people relate to and perceive the environment. Quantitative versus qualitative data. Key differences. Quantitative data. Qualitative data. Expressed in numbers and can be measured. Descriptive and non-numeric, based on characteristics. Allows for statistical analysis. Provides rich, contextual insights but not directly measurable. Can be continuous, e.g., temperature, or discrete, e.g., species count. Categorical or thematic data, e.g., types of pollution or behaviors. Examples: temperature, air quality, species population. Examples: ecosystem health, species behavior, community perceptions. Objective and can be verified using tools and instruments. Subjective, influenced by observation and interpretation. Importance of quantitative and qualitative data in environmental science. Holistic understanding. Both types of data are essential for a comprehensive understanding of environmental issues. Quantitative data provides precise, measurable insights, while qualitative data offers contextual understanding, often reflecting the human or ecological dimensions of the issue. Informed decision-making. Quantitative data supports policy decisions with clear, objective measurements, e.g., pollution levels, while qualitative data informs decision-making by capturing public opinion, ecological health, and broader social impacts. Complementary approaches. The combination of both data types allows researchers and policymakers to gain a more complete picture. For example, quantitative air quality data can be complemented by qualitative data on community health perceptions and local impacts. Previous year questions. Which of the following is an example of qualitative data in environmental science? A. Rainfall measurement in millimeters. B. Soil pH measurement. C. Community perceptions of deforestation. D. Species count in a protected area. Answer. C. Community perceptions of deforestation. Year, 2020. What type of data is typically analyzed using statistical methods such as regression or correlation? A. Qualitative data. B. Quantitative data. C. Both A and B. D. None of the above. Answer. B. Quantitative data. Year, 2021. Which method is most suitable for collecting qualitative data on species behavior? A. Field surveys. B. Remote sensing. C. Laboratory analysis. D. Statistical modeling. Answer. A. Field surveys. Year, 2019. Quantitative data on air pollution is often measured in terms of A. Soil texture. B. Species diversity. C. Particulate matter concentration. D. Community opinions. Answer. C. Particulate matter concentration. Year, 2020. Which of the following best describes the purpose of qualitative data in environmental science? A. To measure pollution levels in numeric terms. B. To capture community values and perceptions. C. To predict future environmental changes. D. To provide statistical analysis of climate data. Answer. B. To capture community values and perceptions. Year, 2021. Which type of data would be used to measure the concentration of pollutants in a water sample? A. Qualitative data. B. Quantitative data. C. Descriptive data. D. Narrative data. Answer. B. Quantitative data. Year, 2020. This lecture explains the core concepts of quantitative and qualitative data in environmental science, detailing their characteristics, methods of collection, and uses in analysis. It also provides key examples and practical applications to enhance understanding, preparing you for the UGC NET JRF exam. You said. Graphical representation. Bar chart. ChatGPT said. Graphical representation. Bar chart. Bar charts are a widely used graphical tool in environmental science and other disciplines for representing data visually. They are especially effective in showing the relationship between discrete categories or groups and their corresponding numerical values. Bar charts allow for clear comparison of data and help in interpreting trends, distributions, and patterns within datasets. What is a bar chart? A bar chart or bar graph is a type of chart that uses rectangular bars to represent data. The length or height of each bar is proportional to the value or frequency of the variable it represents. Bar charts are used for displaying and comparing the frequency, count, or other measures, e.g., mean, sum of different categories or groups. Types of bar charts. Vertical bar chart. Column chart. In a vertical bar chart, the bars are displayed vertically, with the height of each bar corresponding to the value of the variable. Horizontal bar chart. In a horizontal bar chart, the bars are displayed horizontally, with the length of each bar representing the value of the variable. Stacked bar chart. This variation is used to show the breakdown of a total across categories. The bars are divided into different segments, each representing a part of the total. Group bar chart. This type displays multiple bars for each category, used when comparing more than one data series across categories. Components of a bar chart. X-axis. Horizontal axis. The categories or groups being compared are placed along the x-axis. In environmental science, these might represent different types of pollutants, species, or environmental variables, e.g., temperature, rainfall, etc. Y-axis. Vertical axis. The y-axis represents the numerical values corresponding to the categories. This could be measurements like pollutant concentration, population size, or rainfall levels. Bars. The bars represent the data points. The height for vertical bar charts or length for horizontal bar charts of each bar indicates the magnitude of the variable for each category. Labels. The bars are usually labeled with values or percentages that help in understanding the magnitude of the data. How to read a bar chart. Look at the x-axis to identify the categories or groups being compared. Check the y-axis to understand the scale or range of the values being measured. The length or height of each bar gives you the value of the variable for each category. In a stacked or grouped bar chart, identify how the segments or grouped bars compare across categories. Advantages of bar charts. Clarity and simplicity. Bar charts provide a clear and simple way to compare discrete categories. Versatility. They can be used for a wide range of data, from environmental measurements to demographic statistics. Easy comparison. They allow for easy visual comparison between different categories or groups. Highlighting trends. Bar charts can effectively highlight patterns or trends across different categories. Disadvantages of bar charts. Limited to discrete data. Bar charts are best suited for categorical or discrete data, not continuous data. Space consuming. For large datasets with many categories, bar charts may become crowded and hard to interpret. Data simplification. Bar charts may oversimplify complex data, missing nuances or relationships between variables. Examples of bar charts in environmental science. Pollution levels by source. In an environmental study, a bar chart could be used to display the contribution of different sources, e.g., industrial, vehicular, agricultural, to overall pollution in a city. Each bar represents one source, and the height of the bar shows the level of pollution measured in micrograms per cubic meter, microgram per cubic meter. Example. X-axis. Sources of pollution: industrial, vehicular, agricultural, etc. Y-axis. Pollution concentration, microgram per cubic meter. Rainfall distribution by month. A bar chart could be used to represent the monthly rainfall distribution in a particular region. Each bar corresponds to a month, and its height represents the total rainfall for that month, measured in millimeters. Example. X-axis. Months: January, February, March, etc. Y-axis. Rainfall. Species diversity in different habitats. Bar charts can be used to compare the number of species observed in different habitats, such as forests, wetlands, and grasslands. Each bar represents a habitat, and its height indicates the species diversity, number of species recorded in that habitat. Example. X-axis. Habitat types: forest, wetland, grassland, etc. Y-axis. Species count. Deforestation rate by country. A bar chart can display the rate of deforestation in various countries, where each bar represents a country and its deforestation rate measured in hectares per year. Example. X-axis. Countries: Brazil, Indonesia, India, etc. Y-axis. Deforestation rate, hectares per year. Creating a bar chart. To create a bar chart, follow these steps. Collect and organize data. Gather the data you want to represent. For example, if you are comparing pollution levels by source, make sure you have the exact numerical values for each source. Choose the right type of bar chart. Decide if you need a vertical, horizontal, stacked, or grouped bar chart based on your data. Label axes and data. Clearly label both axes with the appropriate categories, x-axis and values, y-axis. Also, label each bar with the corresponding data value if necessary. Choose a scale. The scale of the y-axis should be chosen to accommodate the range of data values. Interpret the chart. Once the chart is created, it can be analyzed for trends, comparisons, and insights. Previous year questions. Which of the following is true about bar charts? A. They are used to represent categorical data. B. They are best suited for continuous data. C. Bar charts are useful for showing correlations between variables. D. Bar charts cannot represent data in a vertical format. Answer. A. They are used to represent categorical data. Year, 2020. In an environmental study, a bar chart representing species diversity in different habitats would have which of the following on the x-axis? A. Species count. B. Habitat type. C. Pollution levels. D. Monthly rainfall. Answer. B. Habitat types. Year, 2019. What type of data is most commonly represented by a bar chart in environmental science? A. Continuous data. B. Discrete categorical data. C. Temporal data. D. Experimental data. Answer. B. Discrete categorical data. Year, 2021. Which of the following would be best represented using a stacked bar chart in environmental studies? A. Total deforestation rate by country. B. Monthly temperature variation. C. Species diversity in a forest. D. Contribution of different pollution sources. Answer, D. Contribution of different pollution sources. Year, 2020. In a bar chart, the y-axis typically represents a categories or groups B, the frequency or value of data C, time periods. D. None of the above. Answer, B. The frequency or value of data. Year, 2019. Bar charts are an effective and versatile tool for visualizing and interpreting environmental data. By organizing and comparing categories, they make complex data more accessible, aiding in decision-making and understanding environmental trends. You said, histograms. ChatGPT said, histograms. Histograms are one of the most widely used graphical representations for displaying the distribution of a dataset. They are particularly useful in environmental science for understanding the distribution of continuous variables such as temperature, rainfall, pollutant concentrations, or species size distributions. A histogram is a type of bar chart that represents the frequency of continuous data within certain intervals or bins. What is a histogram? A histogram is a type of graphical representation that shows the frequency distribution of a continuous variable. The data is grouped into intervals, also called bins, and the height of each bar corresponds to the number of data points that fall within each interval. Unlike bar charts, which display categorical data, histograms are used for continuous or interval data. Components of a histogram. X-axis, horizontal axis. The x-axis represents the range of values for the variable. This axis is divided into intervals or bins. For example, if you are measuring pollutant concentration, the x-axis might represent ranges of concentration levels, e.g., 0-10 micrograms per cubic meter, 10-20 micrograms per cubic meter, etc. Y-axis, vertical axis. The y-axis represents the frequency or count of data points within each bin. It shows how many data points fall into each interval on the x-axis. Bars. Each bar in the histogram represents the frequency of the variable within a specific interval. The height of the bar indicates the number of data points in that range. How to construct a histogram. Step 1. Collect and organize the data. This could be a dataset of pollutant concentrations, species sizes, or rainfall measurements. Step 2. Determine the range of the data and divide it into intervals or bins. The number of bins should be chosen carefully to avoid under or over smoothing the data. Step 3. Count how many data points fall into each bin. Step 4. Draw a bar for each bin, where the height of the bar corresponds to the count or frequency of data points in that bin. Step 5. Analyze the histogram to understand the distribution of the data. Types of histograms. Uniform histogram. In a uniform distribution, the frequency of data points is evenly distributed across all intervals. All bars have approximately the same height. Normal distribution. A normal distribution is symmetrical, with most of the data points clustering around the central value, and fewer data points appearing as you move further from the center. The histogram would resemble a bell curve. Skewed distribution. In a skewed distribution, the data points are not evenly distributed. A positively skewed histogram has a longer tail on the right, while a negatively skewed histogram has a longer tail on the left. Bimodal distribution. A bimodal distribution has two distinct peaks, indicating that the data may come from two different underlying distributions. Advantages of histograms. Clear representation of distribution. Histograms provide a clear visual representation of how the data is distributed. They show where data points are concentrated and where there are gaps. Handling of continuous data. Unlike bar charts, which are used for categorical data, histograms are ideal for continuous data. Identification of patterns. Histograms help identify patterns such as normal distribution, skewness, and the presence of multiple peaks in the data. Disadvantages of histograms. Loss of individual data. Histograms do not show individual data points, only the frequency of data within intervals. As a result, important details about specific data points may be lost. Bin size sensitivity. The appearance of the histogram can change depending on the size of the bins chosen. Too few bins may oversimplify the data, while too many bins may make the histogram appear noisy. Does not show outliers. Histograms do not provide direct information about outliers or extreme values, which might be important in environmental data analysis. Examples of histograms in environmental science. Pollutant concentration distribution. A histogram can be used to visualize the distribution of pollutant concentrations in a city. For example, if you are measuring air quality, you might create a histogram that shows the frequency of various concentration ranges of pollutants like PM2.5, NO2, or CO. X-axis, pollutant concentration, microgram per cubic meter. Y-axis, frequency, number of days with a specific concentration range. Rainfall distribution. A histogram can be used to show the distribution of annual rainfall amounts in a particular region. The intervals on the x-axis could represent ranges of rainfall, e.g., 0 to 100 m, 101 to 200 m, and the bars would show how many years fall into each range. X-axis, rainfall Y-axis, frequency, number of years. Species size distribution. A histogram can be used to represent the size distribution of a particular species in an ecosystem. For example, you could show the distribution of body sizes of fish in a river, with bins representing different size ranges. X-axis, fish size, cm. Y-axis, frequency, number of fish. Temperature variations. A histogram can be used to show the distribution of temperatures in an ecosystem over the course of a year. The intervals might represent temperature ranges, e.g., 15 - 20 degrees Celsius, 21 - 25 degrees Celsius, and the height of the bars would show how many days had temperatures in each range. X-axis, temperature, degree C. Y-axis, frequency, number of days. Creating a histogram. To create a histogram, follow these steps. Prepare your data. Gather the continuous data you want to analyze, e.g., pollutant concentrations, temperature readings. Choose intervals. Divide the range of the data into equal intervals or bins. The bin width depends on the data's range and the level of detail you want. Count data points. Count how many data points fall into each bin. Draw the histogram. Create bars where the height of each bar represents the frequency of data points within each interval. Analyze the distribution. Once the histogram is complete, analyze the shape and distribution of the data. Look for patterns such as normal distribution, skewness, or multiple peaks. Previous year questions. Which of the following statements about histograms is true? A. They represent categorical data. B. The x-axis is used to represent continuous variables. C. The height of the bars shows the frequency of categorical data. D. Histograms cannot be used to represent continuous data. Answer. B. The x-axis is used to represent continuous variables. Year, 2020. In a histogram of pollutant concentrations, the x-axis represents A. The frequency of pollutants. B. The range of pollutant concentration. C. The specific source of pollution. D. The time of year. Answer. B. The range of pollutant concentrations. Year, 2019. A histogram displaying the distribution of temperatures throughout the year would typically have the following on the x-axis. A temperature ranges. B. Number of temperature readings. C. Daily weather conditions. D. Time of year. Answer. A temperature ranges. Year, 2021. Which of the following is true about the construction of a histogram? A. The bars must always be of equal width. B. The x-axis should represent categorical data. C. The height of each bar represents the frequency of data points in the bin. D. The y-axis should represent the categories being compared. Answer. C. The height of each bar represents the frequency of data points in the bin. Year, 2020. Which type of distribution is most commonly represented using a histogram? A temporal distribution. B. Discrete categorical distribution. C. Continuous distribution. D. Seasonal distribution. Answer. C. Continuous distribution. Year, 2019. Histograms are essential tools for visualizing continuous data and understanding its distribution. By grouping data into intervals and analyzing the frequency of values within each range, histograms provide valuable insights into the data's characteristics, which are crucial for decision-making and analysis in environmental science. You said, pie chart. ChatGPT said, pie chart. A pie chart is a circular statistical graphic that is divided into slices to illustrate numerical proportions or percentages. Each slice of the pie represents a category, and the size of each slice is proportional to the percentage or count of that category relative to the total. Pie charts are often used in environmental science to represent data that is divided into categories, such as pollutant sources, land use distribution, or species composition in an ecosystem. What is a pie chart? A pie chart is a visual representation of data where the circle is divided into slices. Each slice corresponds to a category of data, and the size of the slice is proportional to the value or percentage it represents. The total of all slices is equal to 100%, making the pie chart a useful tool for showing the relative proportions of different categories in a dataset. Components of a pie chart. Circle. The entire circle represents the whole dataset, 100%. Slices. Each slice represents a specific category within the dataset. The size of the slice corresponds to the proportion of that category relative to the total. Labels. Each slice is usually labeled with the name of the category and the labels. Each slice is usually labeled with the name of the category and the percentage or count it represents. Legend optional in some pie charts. A legend is included to clarify the meaning of each slice, especially when there are many categories. How to construct a pie chart. Step 1. Identify the data categories you want to represent. For example, if you are analyzing the sources of air pollution, the categories could be transportation, industry, and residential. Step 2. Determine the total amount or percentage for each category. This could be in terms of count, frequency, or proportion. Step 3. Calculate the angle for each slice. The angle of each slice is proportional to the percentage of the category it represents. The formula for the angle of each slice is angle of slice equals category value total value times 360 ring operator. Angle of slice equals total value category value times 360 ring operator. Step 4. Draw the circle and divide it into slices based on the calculated angles. Label each slice with the appropriate category and percentage or count. Step 5. Analyze the pie chart to understand the relative proportions of each category. Types of pie charts. Standard pie chart, the most basic form, with a single circle representing the entire dataset divided into slices. 3D pie chart, a three-dimensional version of the pie chart that adds depth to the presentation. However, it may distort the relative size of the slices and is not recommended for precise data comparison. Exploded pie chart. This variant explodes or separates one or more slices from the rest to emphasize specific categories. Donut chart, a variation of the pie chart where the center is hollow, creating a ring shape instead of a solid circle. This is often used when multiple datasets need to be displayed in a single chart. Advantages of pie charts. Simple visualization. Pie charts provide a clear and simple way to show proportions or percentages in a dataset. They are easy to understand at a glance. Effective for showing parts of a whole. Pie charts are especially useful when showing how individual components contribute to a total, such as in environmental studies where data might be divided into various categories like pollutant sources or land cover types. Compact. Pie charts take up less space compared to other charts like bar graphs, making them ideal for small datasets. Disadvantages of pie charts. Limited data representation. Pie charts are best suited for datasets with relatively few categories, usually no more than 6. Too many slices can make the chart confusing and hard to interpret. Difficulty in comparing slices. It can be difficult to accurately compare the sizes of slices, especially if they are similar in size. For more precise comparisons, bar charts may be a better choice. Lack of detail. Pie charts only show the proportions of categories but do not provide detailed numerical data, which may be necessary in some cases. Examples of pie charts in environmental science. Pollutant source distribution. A pie chart could be used to represent the sources of air pollution in a city. For example, the chart might show the percentage of pollution attributed to different sectors such as transportation, industrial activities, residential heating, and others. Categories: transportation, industry, residential, agriculture, others. Proportion. Each slice of the pie represents the percentage contribution of each source to the total pollution. Land use distribution in a region. A pie chart can also be used to show the distribution of land use in a specific area. The categories might include residential, commercial, industrial, agricultural, and forested land. Categories: residential, commercial, agricultural, industrial, forest. Proportion. Each slice shows the proportion of land allocated to each use. Species composition in an ecosystem. A pie chart can be used to represent the composition of species in an ecosystem. For example, in a marine ecosystem, the chart could show the proportion of different species groups such as fish, algae, plankton, and invertebrates. Categories: fish, algae, plankton, invertebrates. Proportion. Each slice represents the percentage of total species biomass or abundance. Energy consumption by sector. A pie chart can be used to display the breakdown of energy consumption by different sectors, such as residential, industrial, transportation, and commercial. This type of data is essential for understanding energy use patterns and planning for sustainability. Categories: residential, industrial, transportation, commercial. Proportion. Each slice shows the share of total energy consumption by each sector. Guidelines for using pie charts. Limit categories. Use pie charts when you have a small number of categories, usually no more than 5 to 6, to ensure clarity. If you have too many categories, consider using a bar chart. Use percentages. Pie charts are best used when representing percentages or relative proportions. Ensure that the total of all slices equals 100%. Use clear labels. Always label the slices with both the category name and the percentage or count they represent. This will help viewers understand the chart at a glance. Avoid 3D or exploded pie charts. Unless necessary, avoid 3D pie charts as they can distort the visual representation of data. Exploded pie charts should only be used to emphasize specific categories. Previous year questions. What is the primary disadvantage of using pie charts for data representation? A. They are difficult to understand. B. They do not allow for easy comparison between categories. C. They are not effective in representing small datasets. D. They require too much space for presentation. Answer. B. They do not allow for easy comparison between categories. Year 2020. A pie chart showing the distribution of pollutant sources in a city would most likely have which of the following on the x-axis. A. Total pollutant concentration. B. Frequency of data points. C. Categories of pollutant sources. D. Specific pollutant types. Answer. C. Categories of pollutant sources. Year 2019. Which of the following is an ideal situation for using a pie chart in environmental science? A. Showing the temporal change in pollutant concentrations. B. Comparing multiple datasets with different units. C. Representing the percentage distribution of land use types in a region. D. Analyzing the trend of species population over time. Answer. C. Representing the percentage distribution of land use types in a region. Year 2021. When constructing a pie chart, the sum of all slices should equal A 100%. B. The total value of all data points. C. The sum of the category frequencies. D. The mean of all data points. Answer. A 100%. Year 2020. What is the main advantage of using a pie chart to represent environmental data? A. It provides a clear comparison between data points. B. It makes complex datasets easy to analyze. C. It clearly shows the proportional relationship between categories. D. It is ideal for showing trends over time. Answer. C. It clearly shows the proportional relationship between categories. Year 2019. Pie charts are a simple yet effective tool for displaying proportional data. By representing data as a circular chart divided into slices, they make it easy to visualize how individual categories contribute to the whole. However, they are best used for small datasets with a limited number of categories to avoid confusion and ensure clarity. You said, table chart. ChatGPT said, table chart. A table chart, also known simply as a table, is a systematic arrangement of data in rows and columns that facilitates the organization and comparison of information. Unlike graphical charts like pie or bar charts, table charts represent data in a more structured, detailed, and readable format, allowing for precise numerical comparisons across different categories of variables.